In today's class, we are going to learn the concept floating point representation. So in the floating point representation, we have single precision and double precision method. Okay. So we are going to see what is that single precision and double precision. So first of all, before getting into those two, single and double precision, let's see how a floating point representation is represented. Okay. So the floating point number is represented as m into r power e, where m is the mantissa, r is the base, e is the exponent. Okay. So this is how we need to follow this particular representation, and this particular mantissa base exponent is represented in the form of a table where the first block will be sign bit and the next one is exponent and the last one is mantissa. Okay, so this is how it is represented. Now let's take an example and see how this sign bit, exponent and mantissa is represented. Let's take an example. 5.625 of decimal number. Okay. Convert this or represent in the floating point. Okay. So this can be written as 5.625. Okay. So bring this 5 to this side. That means what it is done? 0.5625. Okay. So how many numbers it has been shifted? Only one number shift, right? Okay. Or the one spacing has been shifted, right? That means you need to convert that into right with respect to 10 power 1, where 10 is nothing but the base for a decimal number. And how many shifts it has been done to get into that side? Only one, right? So it is considered as 1. Okay. Now with respect to this, what we can say, the number which is after the decimal point is considered as the mantissa, and the number over here is considered as the base or radix r, and this particular power is considered as the exponent. Okay. So with respect to this, we can write, for a positive number, always sign bit will be 0, and the exponent what we have is 1, and the mantissa what we have is 5625. Okay. So this is how to represent a particular number. Now let's take a binary format and see how to represent the floating point for a binary value. Okay. 101.101. Okay. We need to represent this in floating point. So floating point means what is the given number? 101.101. All these digits move it to this side. Okay. So how many positions it is getting shifted? 3 positions, right? Okay. So what we can write? Point or 0.101101 into 2 power 3. Always remember there should be a digit left before the decimal point. Okay. Once we get into single precision and double precision, I will show you how to leave that particular number. Now, according to this particular representation, this is in the form of m into r power e, where the number which is after the decimal point is the mantissa, and this 2 is the radix or the base, and 3 is the exponent. Okay. Now, we need to represent with respect to sign bit, exponent, and mantissa. So what is the sign bit? As this particular number is positive number, the sign bit will be 0. This is the sign bit. And the exponent will be 3. And the mantissa is 101101. This is the mantissa and this is the exponent. This is how to represent any number. It can be a decimal number or a binary number with respect to floating point representation. Now, these are the basics. Now, let's get into a little bit a deeper concept where we will be considering the floating point representation in single precision and double precision. So let's see the difference between single precision and double precision. Okay. Now let's draw a table. With respect to precision, base, sign, exponent, and significant. Okay, I will tell you what is the significant and all those things. So precision, as I've already said, we have two precisions. One is single precision and another one is double precision. Okay. So for single and double, the base will be almost 2. Okay. And the sign bits will be 1. And the exponent will be, for the single precision, it will be 8-bit, and for the double precision, it will be 11-bit. Okay. And for the significant bit, that is mantissa, the bits will be 23 bits plus 1 and 52 bits plus 1. That is, these are 24 bits and this is 53 bits. Okay. So this is an overview of precision. Now let's see the single precision. Single precision is a format proposed by IEEE for the representation of floating point numbers. It occupies around 32 bits in computer memory. So total single precision will be having 32 bits in a computer memory, in which there will be an sign bit and 8 exponent bits, and the remaining 23 bits are Mantissa bits. Okay, so this is a single precision method. And coming to the double precision, it will have sign bit, 11 bits, exponent, 52 bits, Mantissa. Okay. So for this particular single precision and double precision, we need to calculate the bias. So I will tell you what is this particular bias. While writing with respect to the exponent, we need to consider this particular bias. Take an example and solve the floating point representation with respect to single precision and double precision. Okay. So the question is 12.625 with decimal number. Okay. So first, let's draw a table which can fit up to 10 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So total 10. Okay, so this will be 2 power 5, this will be 2 power 4, 2 power 3, 2 power 2, 2 power 1, 2 power 0, and this is our decimal point over here. Okay. Now let's convert this 12.625 into binary number first. Two 6 are 12, 0, 2 3s are 6, 0, 2 1s are 2, that is 1 left. So 1100. Okay. So before the decimal point, you need to mention 0, 0, 1, 1. This is 1100. And for the remaining boxes, put just 0, 0. Okay. And let's find out the values of 0.65 into 2. 0.625 into 2. Okay. So it will be somewhere around 0.625 into 2. It will be somewhere around 1.25. So take the 1 out and again 0.25 into 2. 0.25 into 2. It is somewhere around 0.5. Take that 0 out and again 0.5 into 2. 0.5 into 2 gives 1. So 101 is the obtained value after converting 0.625. Okay. So 101 and remaining box put 0. So this will be like 2 power minus 1, 2 power minus 2, 2 power minus 3 and 2 power minus 4. So this is the data we got initially. Now we need to find out the mantissa as well as the exponent. Okay. So the answer what we got is 1100.1010. Okay. So we need to convert this particular values. We need to bring these values to this other direction in order to make m into r power e. Okay. So always we need to have one number left before the decimal point. So how it can be written? 1.1001010. Okay. With this, how many digits has been shifted? 3, right? So we can write this as 1.1001010 into 10 power 3. Okay. And this is our mantissa. Okay. With respect to single precision. So for single precision, how we can write? As it is a positive number, sign bit will be 0 and the single precision bit will be, and the mantissa will be 1001010 with respect to how many bits? So we have already written here, right? For a single precision, we need to mention with respect to 23 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So this is how to represent the mantissa. Now, how to write this exponent? How to write this exponent? Now let's see. So we have a formula based on bias. Okay. So this particular bias is represented with respect to 2 power n minus 1 minus 1. Okay. So where stored exponent equal to actual exponent plus bias. Okay. Now let's see first the n. N value is, for an exponent, it is an 8-bit, right? So 2 power 8 minus 1 minus 1. Oh, that means 2 power 7 minus 1, which is nothing but 127. Okay. Now, the bias what we got is 127. Okay. The bias what we got is 127. And already the exponent what we have is, exponent what we got is how much? See here. 10 power 3. That is, 3 is the exponent, right? 3 is the exponent. So what we can do? 127 plus 3, which is nothing but 130. So this is the value what we got with respect to the formula of the bias. Okay. So let's take the binary value of 130. 2 6 are 12. 2 5 are 10. 0. 2 3 are 6. 2 2 are 4. 1. 2 1 are 2 3. 2 6 are 12. 0. 2 8 are 16. 0. 2 4 are 8. 0. 2 2 are 4. 0. 2 1 are 2. 0. So the answer what we got is 1, 1, 2, 3, 4, 5, 1, 0. Okay. So this is the answer what we got. So the exponent value will be, so sin bit is already 1. Sin bit is already, as it is positive number, so the sin bit will be 0. If it is a negative number, it will be 1. And the exponent what we got over here is 1, 1, 2, 3, 0, 0, 1, 0. This is the 8-bit exponent what we got. And the remaining number what we got is 100101 with respect to 23 bits. 100101. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so this is Mantissa. This is 23 plus 1 bit. And this is 8-bit, which is exponent. And this is sin bit. Same pattern is applicable for the double